Awesome. Sorry for the delay. Let's begin. I'll just talk really quickly so we can make up time.
Take your time, though.
Okay, I'll take my time. So my name is Matt Swoboda, and I'm also known as Smash of Fairlight from the demoscene. I currently work at a company called D3 Technologies, which is in the live shows, concerts, and so on, visuals market. I'm here to talk to you today about real-time ray tracing, which, when you think about what they showed in the keynote, probably seems quite basic and so 10 years ago. But the difference between what I'm going to talk about today and what they talked about in the keynote is that my goal is to make a ray tracer that is really real-time for real-time applications. Ray tracing is a very important part of computer graphics because it solves a number of very hard problems quite elegantly and simply. Problems that traditional rasterization pipelines always have to fake. Things like refractions and refractions, global illumination, area lights, soft shadows, things that are challenging to do with a traditional real-time rendering path. But ray tracing has always been slow or impractical for real-time applications. A lot of the research in the ray tracing space has been focused on offline rendering. There's been an awful lot of work gone into optimizing ray tracing over the years, but most of it has been aimed at an offline rendering context or a production context and making that more efficient. And when you're dealing with that kind of world, you're dealing with very complicated scenes with an enormous number of rays. And often you start considering things like distributed computing or making a very, very long render time slightly less long. So there's been a lot of valuable work, but it's kind of biased to something that was already very, very slow. It means that the data structures that you're able to work with can often be generated quite slowly and optimally because you're going to cast so many rays that it's not really worth worrying about. Real-time ray tracing, on the other hand, has often been limited to very specific use cases. There's been demos, like demoscene demos, which have done real-time ray tracing for many years, and they often involved massive amounts of hacking, or they only handled spheres, or they only handled static scenes. There's been a lot of work with, there's been many real-time ray tracing applications over the years, but they always have certain limitations which make it impractical for production, or they only handle a certain effect or a certain use case. We want to do something that's actually usable for production. Then there's this issue of interactive ray tracing. There's a lot of modern ray tracers in graphics packages now, and there's some really good quality ones like Arion, like Brigade, Optics. There's a whole wealth of really good quality ray tracers which can run real time, but they're still designed for production offline rendering, I guess. And they can do real time, but the frame rate is more interactive than real time. It's 5 frames a second rather than 30 or 60. And they often allow certain things, like the scene is allowed to be static. They allow multiple frames to refine. They themselves impose limitations, which mean that if you wanted to do something completely real-time, you'd still be limited. So what does real-time actually mean when it comes to our goals? A production-usable real-time ray tracer handles fully dynamic scenes, not just rigid objects, but scenes where all of the triangles change every frame. I do a lot with like meshed fluid dynamics or dynamically generated procedural meshes, and they have no coherence over frames. The triangle set is completely regenerated, which means that the data structure has to be completely regenerated. Production usable also means fully dynamic cameras, fully dynamic multiple light sources. And it needs to be good quality and low noise at 60 frames a second, or perhaps at anywhere from 15 to 60, depending on your your perception of real time and how much you care. So we need a technical approach that's a little bit different to the sort of the standard offline, the standard real interactive ray tracer. So here are my short list of requirements for what I wanted to be able to do. First thing, I wanted to be able to support actual triangles, not distance fields, not voxels, not primitives, but actual triangles, what you get out of a 3D package or what you generate from marching cubes or something like that. And I wanted to be able to intersect those perfectly accurately. So I wanted to be able to handle triangles natively. Triangles are a really useful thing because they store a lot of data very efficiently. Things like UVs, normals, color data, and materials are all very easy to handle in triangles, and there's a long production pipeline to handle them. I wanted to be able to support enough triangles to actually be usable for something decent. I wasn't going to aim for millions and millions of triangles because I didn't need it. I reckon I needed about between 10K and 1 million. Probably a good middle ground would be a target of around 100K triangles. With 100K triangles, you can do a decent real-time rendered scene. You could do a decent game scene, for example. I wanted to support a decent size of scene. I didn't want to have to support infinite landscapes or anything like that, but something that was usable for an actual production shot, like a room, something like that kind of size. I obviously needed to be able to handle enough rays that I could actually do something with it. So I kind of guessed that if I could do more than 1 million per frame, I'd probably be in a good basic place to be. And I was going to target a consumer DX11 GPU. So we're talking like 680, 780 territory, not network of Titans territory. So first thing I considered was the data structure. And we already know that the best data structure to use for ray tracing is a bounding volume hierarchy, because smart people have done a lot of research into determining this. And they've determined that BVH is the most performant structure for GPU-based ray tracing. They're memory efficient, and they're good at rejecting rays that miss quickly. This is an example of a BVH that I stole off the internet. So you can kind of see how there are big bounding boxes that are refined into smaller ones, meaning that you can quickly reject rays that miss just by testing high-end parts of the tree, and you can skip down as you get closer to the actual surface. This is a good hierarchical structure. But what does performance actually mean? We know that BVH is very efficient to trace, but is it enough just to consider how many rays you can process through the structure? No, of course it's not, because we've got a real-time application here. We throw away the data structure every frame because our scene changes completely every frame. So that means that the data structure has to be considered to be generated as part of the frame. The execution time is not just how long the rays take, it's how long the data structure takes to generate, plus how long it takes to cast the rays. The BVH might be very fast to cast rays through, but the generation is quite slow and painful. It's reasonably easy to generate a very bad BVH. It's quite hard to generate a very good BVH. They're hard to update incrementally. They're reasonably hard to generate on the GPU. It's an active area of research. The point is that if I want to achieve this 30 hertz ray tracer, then I have 30 milliseconds to do everything. I'm probably going to be spending quite a lot of that casting rays. So I need to be doing this in a few milliseconds. I don't have time, probably, to generate a BVH of any quality for the kind of scene that I'm talking about. So let's go back and revisit the data structures and pick a structure that's actually really easy to generate on the GPU in real time. If we start by thinking about how fast it is to generate rather than how fast it is to trace, we might come up to a better starting point. And the simplest structure you can possibly think of is a grid, a voxel grid. Store a list of triangles in each cell of a uniform grid and store which triangles intersect each cell. Obviously, this is sort of 1960s wisdom here. And conventional wisdom says voxel grids are slow, memory hungry, inefficient, wasteful. But let's just ignore that anyway, because they're very, very fast to generate. We can effectively rasterize our scene into the grid and instantly have a data structure that we can use for ray tracing. The other thing about BVHs is that actually they're very efficient, but they're not particularly well mapped to the GPU. I think I'm in the wrong conference to be lecturing about how GPUs work and what the most efficient thing to do is. So suffice, BVHs do have issues with divergence, that a voxel grid is simple to trace because you have a shader that uses very few registers, it's very low divergence, very simple. There's no need for a stack in the shader, there's no need for any local memory to be used. And it means that you can make a very simple shader to trace them. Unfortunately, we're talking about a production ray tracer. And a voxel grid is an elegant solution for around 1,000 triangles and a small scene. But when you expand the scene size and you bump up the triangle count, it doesn't scale very well at all. There's no skipping of empty space. You either need a very high-res grid to store the triangles with any sparseness, or you have too many triangles per cell. So either you're going to blow all the memory on the grid, or you're going to blow all the rays on triangles in one cell. So there's a kind of a refinement of the voxel grid is a brick map. A brick map is basically a two-level voxel grid. There's a low-resolution uniform grid, and each cell, if it contains anything, contains a pointer to a high-resolution mini cell, a brick. So it's sparse. Bricks are only allocated where geometry occurs. It means that you can get a much higher effective resolution because you only need to store the areas of the grid that are actually used. And it means when you're tracing them, you can skip over empty space. But it's still very fast to generate. You can still effectively rasterize your geometry into them. Here's an example of a brick map. So as you can see, there are high-resolution cells stored around the actual model, and the ones further away are sparse. It's very easy to generate in 3 passes. You just render the geometry at a low resolution to mark the cells that are used. Then you allocate bricks for each filled cell, and then you re-render the geometry at higher resolution, filling the bricks where they occur. So it's very quick, and the good thing is you could use compute, or you can use the piece of hardware which is already designed for this purpose and rasterize them. So brick map generation with 100K triangles, and I can get an effective resolution of 256 cubed, which gives a reasonable spacing for a typical scene. I mean, again, I'm talking about a production, reasonably well manicured scene, so I don't need to worry about someone modeling a 1 million poly wheel of a car and sticking it in one grid cell, because we can assume that that when it's been worked with, it's done with a degree of effort to optimization. So in this case, I can get typical generation times for the whole data structure of under 5 milliseconds per frame, and it is often on a decent high-end machine, and for a reasonably well-made scene, it can be 1 to 2 milliseconds for the whole scene. This actually makes it practical, but it's the kind of cost that it means it's not a great pain to you. Go away. So brick map tracing. The performance depends not only on the number of triangles, but the length of the rays. This is one downfall of brick map tracing compared to BVHs, which are relatively agnostic to how far the rays travel. The main issue, I suppose, we have with shader programming is not the length of the shader, it's the amount it diverges. You can always throw more cores at a long shader or lots of instances of a shader, but when you have heavy divergence, then you start wasting your time a lot. Does everyone know what I mean by divergence? Does anyone want me to explain what I mean by divergence? Okay. What I mean by divergence is when you have a bunch of threads inside one, we're green, aren't we? So we call them warps. Inside one warp, they all execute the same code in lockstep, or at least on maybe the latest hardware has got smarter, but up until the generation I understood, which is PS4 and modern DX11, they all execute the same shader code in lockstep. So when you introduce branches or loops, unless every thread inside that warp takes the same path, then you're going to have threads going idle while other threads are working. This is divergence. So if you have like a BVH trace example, and half of your threads go one way in the shader through a branch, half go the other way through the branch, then what you effectively end up paying for is the execution time of both those things added together. So in that case, branches become very efficient. Similarly, if I've got a bunch of threads all taking different loop iteration counts, then the cost you will pay is the worst. It doesn't matter if like 31 of your threads take one iteration. If one of them takes 100, you pay for the 100. This is why divergence is important. This is why a lot of work has to go into making your shaders efficiently work by all able to occupy the shader all the time evenly. So this is a load balancing issue. The good thing about brick map tracing is it's stateless. BVH tracing involves a tree traversal. And to traverse a tree, you need some form of stack. You can do a stackless BVH trace, but it resolves to a linked list. So actually it ends up that you step a lot further through the tree. Brick map tracing is stateless, which means that at any point, given any position, you can work out the leaf node without requiring any state. You don't need to walk down a tree to find it. You can instantly get there. What that means is that if I'm tracing a ray, I can change the direction of the ray, and where I am in the structure, where I have reached, is still valid. I don't need to start from the leaf, from the top level, to be able to continue tracing the ray again. So I can bounce and bend rays easily just in a ray tracing loop. So what we can do is you can use this to load balance a large number of ray tracing jobs. If I need to cast lots and lots of rays, I can put them all in a queue. And even if some of them complete before others, if one of them completes early, it grabs another one off the list and keeps going. So in summary, I implemented this, and I tried to work out what I could actually do with it. And I worked out that I could get 1 billion rays a second on my consumer GPU. 1 billion rays per second. This is quite good. I mean, this sounds like a lot of rays, right? But it turns out that how many rays is 1 billion rays per second? What does that actually practically mean? If you assume 1 million pixels per frame, or 2 million if you're full HD, and 30 frames per second, which is a reasonable real-time goal. But you can't blow the entire budget of the frame because you want to do post effects, and you need to generate the structure, and you need to do some other work. So you're giving yourself half the frame time. It works out that you get 16 rays per pixel per frame, which is really, that is not a very big number at all, a very small number. So what can you do with 16 rays per pixel per frame? Well, let's talk about the natural applications of ray tracing that we originally wanted to do. Ambient occlusion, 16 rays is going to be a very noisy looking ambient occlusion. Ambient occlusion starts looking good around 100 rays. Path tracing starts looking good probably about 1,000 rays. Soft shadows, maybe soft shadows. You can probably do, with a nice jitter pattern, you could probably get close to a good looking soft shadow with 16 rays. Accurate hard shadows, hard shadow can be traced with 1 ray per pixel per light. Practical application. Reflections, hard reflections and refractions can be traced with 1 ray per bounce. So again, practical application. And obviously primary rays, camera rays, can be traced with 1 ray. So we'll go through a few use cases. Hard shadows. Here's an image of some hard shadows rendered in the real-time renderer. Hard shadows, 1 ray per pixel per light. Hard shadows are actually quite annoying to do with rasterization. They're quite hard to do, so this is kind of a bonus thing. If you had many, many small point light sources and you didn't want to generate shadow maps for all of them, or like, for example, particles casting shadows, this is a great solution. Reflections. We did a demo last year which featured multi-bounce reflections and refractions. So we can do 4 bounce reflections in a reasonable time. And refractions, we got 12 bounce refractions in this case. So sharp reflections, you only need 1 ray per pixel per bounce. And with a few bounces, you get quite good results. Maybe you only need 1, but with 3, 4 bounces through shiny objects, you get good quality quite quickly. Refractions need more bounces. We use 12, but the rays tend to diverge less, so those bounces are cheaper. We also have a semi-accurate chromatic aberration. It's the GDC people like to call this physically inspired, which means that they looked at a picture of what it was supposed to look like, and then they faked it. I'm quite honest about that. We are physically inspired in that it really does trace 3 things through the objects, but there's still quite a lot of faking involved. But you get good results. And finally, primary and camera rays. Normally, I don't bother tracing camera rays because they're quicker to rasterize. But if you're using warped rays like fisheye, they're quite hard to rasterize. Then it's worth considering using a ray tracer. Bonus cases. It's a convenient way to do CSG accurately, a ray tracer. I always wanted to do CSG for many years. I tried numerous ways of faking it and hacking it and using like marching cubes or using the stencil buffer and so on. Actually, doing the ray tracer is very easy and effective and efficient. We also use them for collision detection for particles. I'm going to try and switch to Team Viewer now. Garg. There we go. And if I go, there we go. So this is an example of hard shadows being rendered with, so these are all real-time lights, but the shadows are ray traced. I'm just going to drag them around a bit. So it's a load of omni lights that cast hard shadows. So it's reasonably effective, frame rate's good. It's running at 186 frames a second or 5.4 milliseconds on the GPU to do that. So that's reasonably effective use. And obviously you can scale up the number quite well. Now we have a breaking wine glass. So this is being traced with, it's really hard to move the camera in Team View because it updates at 5 frames a second. So yeah, as you can see, we've got multi-bounce, reflections, and refractions. And it's reasonably like convincing. It's enough for a real-time application. And what's the other one? This is an example of refractions. reflections, sorry. Runs quite well, multi-bounce reflections through as you can see, the scene is heavily breaking and stuff, so the data structure is changing heavily every frame. That's obviously the other part of the demo. We'll switch back to slides. Cheers. Okay, so next application, moving on to something more interesting, ambient occlusion. The effects we talked about so far, you could fake them with rasterization, although arguably reflections and refractions would be very annoying to do. But ambient occlusion is starting to get something that's actually quite difficult to achieve using traditional ways without a lot of faking. So here's an image of ambient occlusion generated from the Raytracer. Ambient occlusion is global illumination light, I guess you could call it. The idea is that you trace lots of rays, and I know this is very obvious, everyone's probably covered this many times, but you trace many rays in a hemisphere from each pixel. And if the rays make it out of the scene to the sky, then they accumulate light, and if they don't, then they don't. So you get a kind of an idea of how much the sky was visible from each point, basically. You need a reasonable number of rays to do this because otherwise you get noise, and 16 per pixel doesn't really cut it, as you said. So 100 to 500 rays per pixel is where you start looking good. But ambient occlusion is a good simple case to start with. What I'm going to talk about now is all about how you take a ray tracer that works, and but it doesn't quite give you enough rays as you wanted, and start hacking and abusing it so you actually get the results that you were looking for. So ambient occlusion is a good place to start because it's got a number of properties which make it slightly easier to manipulate than true global illumination. Firstly, the result is camera independent. It doesn't matter if you move the camera around, the colors returned do not depend on the camera position. Obviously, the screen changes, but there's no specular effects. They don't depend on the light either, and they don't depend on the material either. So that means that there's much less properties to change to deal with. And the rays are quite cheap. We only care about hit and miss. There's no bounce. There's no surface evaluation. The only thing that matters is whether the ray hits anything or not. And the other thing is the results are quite soft. They're quite diffused and blurry, which means that you're more likely to be able to get away with cheating because the results are soft anyway. So talk about the basic optimizations. I can do 16 rays per pixel. I want to do the appearance of doing 100 or 200. How am I going to do it? First thing, the obvious thing, is to do spatial optimization. So if I've got my screen, instead of tracing 16 rays for every pixel, why don't I subdivide and start tracing, say, loads of rays for every fourth pixel, something like that, and interpolate the results. Or why don't I start subdividing and starting the rays from where the neighbors hit, so I get a cheaper ray? Or why don't I just average out the neighbor's results, or do some sort of blurring or something like that? And all of those actually work for us because we're relying on spatial frequency anyway, high spatial frequency. We're relying on the noise of lots and lots of random rays. If I stick all my rays on every fourth pixel, I still get the same quality as if I just did 16 per pixel and blurred them. So you don't really gain very much from spatial optimization. What about temporal optimization? If we reuse data from the previous frames, then if the frame's not moving, if we just randomly change and average over the frames, if we randomly jitter the rays and blend them over frames, then what you refine to is the right result. You refine to as if you trace loads and loads of rays in one frame, which is great, except obviously if the scene's not moving, the camera's not moving, then It's not really the most interesting production case in the world. So we obviously have to handle moving cameras somehow. So this is where temporal reprojection comes into play. Temporal reprojection is where you have the current frame and you've got the depth buffer, so you know where the pixel is in space, in world space. And you invert the camera transform and you go back to work out where it was in the previous frame's screen position. So you can track it through space. Similar idea to camera-based motion blur, really. So if you know where the pixel was in the last frame, you can sample its ambient occlusion result from there, which is great, but obviously the thing's changing, so you need to be able to wait out values which didn't exist in the previous frame or did exist in the previous frame and don't exist in the new frame. So you need to be able to work out if a sample really did exist. Here's an example. This is temporal reprojected ambient occlusion generated from the Raytracer. And that's what it looks like when it moves. So you can see artifacts here, here. You can see some blurring here where it's missed. You can see how the temporal reprojections work pretty well, but there are obvious errors being introduced by the reprojection step. It's got more noisy. There's a number of things that we try to do to improve it. Where we find that we miss a load of information and we've got a load of new information, we chuck more and more rays at that point. So this is something that's very easy to do with a Raytracer, which is a nice quality of it. Where I've got errors, I use like 100 rays per pixel, but only for the error cases. So I get this kind of, I fix up my holes very quickly. But it still has problems. It's still not perfect. It's quite hard to tell if the pixel in the previous frame really is the pixel you've currently got without some very, very clever schemes. And obviously, this only works for dynamic scenes, for static scenes. This only works for camera movement. I've got dynamic scenes. I want to move stuff. So what do you do with the dynamic scene? You can generate motion vectors. This is something that we use for screen space motion blur already, that I'm sure many other people have. So we already know approximately where a whole object was in the previous frame. And we can add that into the temporal reprojection step. And that means that we can track an object through space. So we can reproject its ambient occlusion properly. The problem is that some of the objects I'm dealing with, like fluid meshing and so on, they didn't exist in the previous frame. They change with the time. So in that case, I don't have any motion vectors. So it doesn't really work. It's not something I can rely on. I'm trying to investigate ways of generating motion vectors for everything, but ultimately it means that it's something that does work for slow-moving content. Another issue is that when content moves fast, it's more likely to get obscured and occluded in different ways, which means that I'm less likely to have a previous frame's correct value for it, so I get more and more errors. And obviously, if I'm reprojecting a value from something that's moving, if I reproject the ambient occlusion of something over here, and then it moves over here, it might have had more ambient occlusion over here. It might have moved into the open world, and so the values I'm reprojecting are wrong. But as we always say in real-time graphics, if it looks okay, who cares? Does it matter? So optimizing ambient occlusion rays. Ambient occlusion, as I said, it doesn't care that much about accuracy because the result's so diffuse and it's not really looking at the surface. So we can start messing with the raycaster to cut bits out, make it less accurate but still good enough. For one thing, we only need to return hit and miss. We don't need to return any proper values. And also, we can cut out the triangle tests. So we only intersect triangles very, very close to the surface we're casting from. As we get further away, we just test voxels. So that's a simple step to speed it up. We don't need to be that accurate about the rays. The other thing we can do is just shorten the rays a lot. If we don't need to cast all the way to the sky, we can just cast a few meters and it will probably be good enough because the way the result diffuses a lot. So in results, we get, with a hacked raycaster that we've messed around, we managed to get from 16 to 32 rays per pixel. By optimizing heavily enough, we managed to double the number of rays. And then we've added a big temporal reprojection step. And what that has given us is something that's actually viable just about for production use. Can I switch to team viewer again? No. No. Yeah. Sorry, it takes a bit of time to load. Right, let's go change the standard exclusion mode. It's really annoying here. Right. Huh? So here I have, so this is a real-time rendered ambient occlusion scene. As you can see, I can move around it, and it's actually maintaining itself. Oops. Yeah, this is actually being used in production here. As you can see, it does a reasonable job of maintaining its shading. See, as I'm rotating around, this is all done on screen space. So you get reprojection artifacts if I move fast enough, but in general, it's coping pretty well. Given this kind of static scene, this would probably be good enough for a production case. I could probably blur and add noise enough to get away with it. Anyway, let's quit out that. I'm just going to minimize that. Can we go back to the slides? Right, so moving on to path tracing. Path tracing is kind of the ultimate goal of ray tracing, I guess, in that it unifies the shading path. With path tracing, you get diffuse light is handled, reflections, refractions, multiple bounces, glossy reflections, caustics, everything can be handled by path tracing. It brings everything together. So this is where you want to end up. This is where I want to end up. It means that visually superb results are possible. This is the closest we can probably get to a very, like a top realism renderer. And it's unbiased, so you can cast as many rays, keep refining the results over and over again. The way that is typically achieved is to cast lots and lots of random bouncing rays which bounce off things and accumulate back from where they ended up through their bounces to give you a color. So if I've got a ray that bounces off an object, bounces off another object, and then hits a light, then the color it returns is the light times the thing it bounced off, the other thing it bounced off, and me. So this is unidirectional path tracing. Unidirectional path tracing is where you just trace camera rays. You do exactly what I said. You cast a load of rays from the camera, you bounce randomly off things and accumulate what you've got. You terminate the ray when it either hits a light or the sky dome that it gets out of the scene, or when it hits something enough to make its energy, make its radiance zero. And what you do is you do this, and then you do it again and again and again with different randomness until you get a good result. You need an enormous number of rays per pixel to get a good result with this, particularly for indoor scenes. Because most rays that you cast and bounce don't actually end up hitting anything, they just disappear into space. Or they miss all the lights and they don't actually add anything. Unless you trace them all to infinity, which you probably can't do. So you end up with a lot of wasted rays. Outdoor scenes fare better because you're more likely to end up hitting the sky dome at some point. Photon tracing is the reverse of the idea. You start the rays at the light sources, bounce around the scene, and try and end up at objects that you store the accumulated radiance on, and then you gather up at the end. So bidirectional path tracing is more interesting because this is a solution where you trace rays from both the camera and the light randomly, bounce them both around, and then you join up the paths that you produce. So the idea is that, and this is one of the images you can achieve this kind of nice bounced lighting. So the idea is that this joining paths, this took me a really long amount of time to grasp what it actually meant when I read the papers, but it turns out it's really, really simple. You have an I ray and a light ray. The I ray bounces off stuff, and the light ray bounces off stuff. And then what you do is for each place it bounced, you cast a joining ray from one node in the I ray to a node in the light ray. And then what you end up producing is a complete path from I to light via the bounces. So you produce the path. It's a really, really simple thing, but I couldn't understand the research papers for ages. So what this means is, by doing this, every ray that every path that you're rendering has a pretty good chance of ending up at light because you're explicitly joining rays that came from the light. So performance. So I did some measurements. I tried to do one path per eye pixel per frame, and I allowed them to bounce 4 times. So that alone requires 4 million rays per frame, 4 rays per pixel. I did the same number of light rays. I thought it would be neatly balanced to do the same number of light rays. And I joined each path. So I've got 4 nodes per eye ray, 4 nodes per light ray. That means I could have 16 join rays. So in total, that means I need 24 rays per pixel just to do one path. The point is that while it seems like a lot of rays, you get a lot of value from them. You're more likely to end up with rays that actually accumulate something. So here's how I hacked it to make it actually work. Obviously, I use temporal reprojection, but the trick is that I didn't just reproject the results. I actually tried to reuse the paths. So the idea is, why would you throw away all the stuff you just calculated if it's still valid? What can you reuse from previous frames? The thing to consider is what changes that will break previous frames' data. If I've cast a load of eye rays and a load of light rays through the scene, what would have changed that made those camera rays or those light rays no longer valid? What would have to have got changed? So obviously, if the camera moves, then the eye rays have changed. If the lights move, the lights rate have changed, but the camera rays haven't. They're still good. If the geometry or materials change, everything changes. So what can I do to sort of hack around this and make it work, given what I want to do in production? I've split the path tracing process into eye rays, light rays, and join rays. And I'm going to try and hack each one to make them work. Eye rays can be reprojected to some degree. So if I move the camera, I can probably take an eye ray and work out where it now is in space, as long as the geometry and materials are static. So what I do is I have a big buffer of eye rays, and when the camera moves, I try and reproject those results. I cast new ones as well. I use a rolling cyclic buffer. If the eye rays become invalidated, I don't keep them around, I trace new ones. And then effectively, I do the same with the light rays. I have a large buffer of light rays, but I only cast a few every frame and cycle it. If the lights are changing, then obviously those rays can become invalid. But does it though? I mean, if you move a light, does that mean that every place that light hit and bounced is no longer valid? Well, if the first bounce point is still accessible from the light, then clearly some random value could still give you the rest of the path. So why throw it away? So all you need to really do is take the path and recast the first bounce and see if it's still accessible. Does that even matter, really? I mean, if it's accessible, obviously still correct. If it's not accessible, will you really notice visually? Probably not. But you will notice if the root node, if the light is not updated. So all I actually do is just move the light position in space and let everything else just cycle around. When geometry and material changes, this is the problem case, because this means whole paths get invalidated. It means you pretty much have to throw everything away. But do you though? Probably not, because actually if you just don't handle it and let things update cyclically, you probably get away with it to a certain degree. It's particularly if you pick kind cases. If we do a load of demos where objects turn and move very, very slowly, then probably no one will notice. If you did actually want to solve the problem, then the trick is that, so I'm trying to speed up, I know it's going to kick me out. Yeah. The thing that you want to do is you want to work out which paths were broken by a geometry moving. It's too complicated to determine if a path was broken by geometry moving by recasting it, because you'd have to retrace the entire path. So you might as well have just thrown it away and started again in the first place. So instead, what I do is I simply just use bounding boxes. And if the path crosses a bounding box, then it's thrown away. And if it doesn't, then it's kept. So if only a small part of the scene is moving, then paths that don't go near that area are still able to be retained. What this means is when it comes to reduction, we just try and bias the case to be a bit more kind. Join rays are the final thing. Join rays account for the vast majority of rays that are cast. And we don't cache them because it's effectively would be caching radiance results, which we already have with reprojection. You can hack join rays in a similar way to ambient occlusion. It only matters if you know if they hit or miss. It doesn't matter about accuracy or bouncing or anything. A join ray is just checking if a point was visible from another point. So obviously, we can use the same tricks used in ambient occlusion and just use the voxels in between. The other thing we can do is we can make them shorter. We know that long rays with brick maps are more expensive than short rays. So why don't we just pick paths to join which are a little bit near to each other by sorting and spatially arranging them? Obviously, it breaks the unbiasedness of the path tracer, but again, if it's visually okay, do we really mind? So with the hacked performance, I have more eye rays per pixel because I found that this is like a major quality differential. I have them in a cyclic buffer, and they update slowly, and as much as possible they're cached. Light paths as well, as much as possible, are cached. They cycle very slowly. Light rays, by not moving lights too quickly, I can easily get around the issues of having to regenerate light rays. And finally, I have an awful large number of join rays. Finally, when it comes to this kind of thing, the right result is not the correct one. The right result is the one that is acceptable enough that you can get away with it. So the extent of the tricks and the cheating and the hacking you can do depends on the use case. So the best thing you can do is just design a nice use case. Either have a nice moving camera and everything else is static, or you have moving lights and the camera moves very slowly, or you have geometry moving but everything else is kind of not really moving very much. If you have crazy moving cameras, lights, and geometry, your scene's probably visually going to be an incoherent mess. So in a way, this constraint is doing you a favor. So maybe the conclusion I reached is that production usable in this context, it depends on the production. If you do a production which is suitable for this kind of thing, then this is production ready. If not, maybe it's not. And finally, I did get to the end. I only overran by about 10 minutes. So thank you. If there's any questions, please.
If you do have questions, raise hand. I have a microphone. Anyone? Okay.
Yeah, so you use rasterization to generate the brick maps. So it's obvious how to do that in 2D. In 3D, you have to use the depth buffer, right?
No.
But how do you go about in 3D to do that?
So there's two ways. The simple rasterization way is you have a geometry shader. Geometry is slow. If you use a geometry shader, what you do is the vertex shader gives the geometry shader the triangle. The geometry shader outputs multiple copies of the triangle in a bound box in space, given the bounds of the triangle. And then this is passed up to a pixel shader. And the pixel shader can assign the triangle to the right slices.
So it's kind of a hybrid.
Yeah. You can do in compute as well, but the problem with doing it in compute is that you get a vastly differing amount of workload depending on the size of the triangles. In a way, you feel a bit dirty using a geometry shader because you know how badly they're going to perform. And I guess you could probably do it nicely with a compute front end on thing. But the thing is, if you've got the rasterization hardware, it's designed to spread workload evenly with a. Yeah, exactly. So why reinvent it?
Anyone else?
Have you used these latest techniques you described for any actual productions outside of the demo scene?
To be announced.
Anyone else?
Could you get good results by computing ambient occlusion on a per vertex basis and then just interpolating across them?
We have that option, actually. I tried it. The problem is that it really depends on the scene whether it looks good. And also, the vertices are quite annoying places to trace from because they belong to several triangles. It's hard to easily determine if a vertex hits because it's obviously the singularity between. But anyway, yeah, it does work, but it's really, really scene dependent. If you've got widely varying tessellation, then it breaks down. I mean, if your scene is made for it, it's an easy case to do. Yeah, definitely. We have light map mode as well, and so we can use light maps to vertex, or have this nice flat shading mode as well, where you do a load of rays on a triangle and just do accumulate the result. And we have the camera mode.
So anyone? Okay.
It seems like the software you do is a lot of computing. Your current software is VJ projection mapping oriented, and I'm wondering if there's applications for this that are really useful for projection mapping and figuring out physical spaces and lights and lenses and things.
Yeah, most certainly is. Yes,
Okay.
Definitely.
And you don't want to go into it at all, or?
It's got a lot. It's definitely got a lot of applications. Yes, I completely agree with you.
So maybe last question, someone? No, in that case, Matt, thank you. It was great.